Suppose that we want to figure out what the enthalpy of reaction is for when we have ethine or acetylene gas combust with oxygen to produce carbon dioxide and water vapor. Well, if we perform this in a laboratory as a series of steps, then we know that Hess's law promises us we can add up the enthalpy changes from those steps to get the overall enthalpy change for this reaction. So maybe we can measure the enthalpies for those steps, maybe we already know them. But in a lot of cases, it's going to be kind of difficult to find suitable reactions that we can add together to give us this overall reaction. We need some kind of standardized way that we can approach finding the enthalpy change for this reaction without having to consult, other reactions that we don't know whether or not they're going to be useful to us. So the way we're going to standardize this is we realize that all we really want to know is this difference here. We don't actually care what this energy value is or this energy value is. We just care what the difference is between them. That's our enthalpy of reaction. So if we could measure this enthalpy from some standard position and this enthalpy for some standard position, then it wouldn't really matter what values we got as long as they accurately represented this difference. So what we can do, we can just arbitrarily define a point where we have elements in their most common stable form. So we can form this CH2 and O2 from carbon and oxygen and hydrogen. Same for this CO2 and H2O. And let's just call this energy level 0. Now if we measure the difference between this and this, and we measure the difference between this and this, then we can follow this for our first step, and then go up for our second step, and that will give us this, according to Hess's law. So that's exactly what we're going to do. So we're going to call these enthalpies of formation because we are forming substances in this step from these elements down here. And we're going to define that the change in enthalpy formation for these elements in their most common stable forms is 0 kilojoules per mole. Now it does have to be the elements in their most stable form. So it has to be H2 gas, can't be H2 liquid, or monoatomic hydrogen gas. Both of these will have enthalpies different from 0, measured relative to this enthalpy value, which is defined to be 0. Now, a note here on this little circle, this means everything's in its standard state. So all the substances are at a temperature of 298.15 Kelvin, according to most references. 1 atmosphere of pressure, 1 molar concentration. And if we change these quantities, then that will affect the enthalpies. So our tables, we're all going to tabulate at these temperatures and concentrations and pressures. And then if we're at a different concentration or a different pressure or a different temperature, then we'll have to modify the values. Now, if we don't have elements, then the enthalpies of formation of our other substances are going to be the enthalpies of reaction when they are formed from the elements. So, for example, the enthalpy formation for methane. Methane has carbon and hydrogen in it. So we would perform this reaction where we combust carbon and hydrogen to produce methane and measure the change in enthalpy. Remember over here, this is all defined to be 0. And so whatever that change is for the reaction is also going to be our enthalpy of formation for methane. It turns out to be minus 74.6 kilojoules per mole. So that's telling us basically what this distance is, or what this distance is, to form these from the elements, or to form these from the elements. And now our last step is we add those steps together to get this value. So that's just Hess's law. So we're going to take the sum of all the enthalpies of formation for the products and subtract then all the enthalpies of formation for the reactants. And the total difference is going to be our difference in enthalpy for the reaction. And this is just applying Hess's law. Let's say that we want to figure out what the change in enthalpy is when we combust acetone, so what makes up nail polish remover, under standard conditions, so our 298 kelvins and our 1 atmosphere pressures and 1 molar concentrations. Well, the first thing that we're going to need here is a balanced reaction. So we're combusting our acetone with oxygen, probably. And when we do that, the carbons are going to convert into carbon dioxide, and the hydrogens are going to convert into water. And some of these oxygens come from the acetone, and some of them come from the oxygen in the atmosphere. Now, if we balance this out, 3 carbons here, 3 carbons here, 6 hydrogens here, 6 hydrogens here, 9 oxygens here, 9 oxygens here. So it's a good balanced equation. Now we're going to look up the enthalpies of formation for these substances. Now the phases are important. It matters whether we have a gas or a liquid or a solid or some different form. And so we want to make sure we look up the enthalpy of formation for liquid acetone. And we find that's 248 minus 248 kilojoules per mole. Now if we try to look up oxygen here, we're going to run into some trouble. We're not going to find it in our reference. And the reason we're not going to find it in our reference is because this is an element in its most common stable form, O2 gas. That's how we usually find oxygen. So that's just defined to be 0. And most references aren't going to bother to write it in. They're just going to assume that you know that. And we also look up the enthalpies for our carbon dioxide and our H2O. This is a gas and this is a liquid. And now we're going to plug them in to our Hess's law equation. Now the stoichiometry is important. That's why we had to write the balanced reaction. So if I have 3 of my CO2s, then I'm going to multiply that by 3 when I'm adding up the enthalpies of formation of the products, since there are 3 of them. Same thing for my CO2s. So here's my H2O, here's my CO2s. And then I'm going to subtract everything from the reactant side. And we had 4 oxygens, and those were defined to be 0. And then we had our 1 acetone, which was minus 248. Crunch all this, and we get minus 2,092 kilojoules per mole. So this is a very exothermic reaction. That makes sense. Combustion reactions tend to be heavily exothermic.